Hi, it's Scientifically Speaking here, and today we are going to dive into the topic of methemoglobinemia. Oh, it's so hard to pronounce for me. Literally, I've tried like 20 times before this, so this is the best I could do. Well, I'm not gonna prolong it anymore, and let's get right into it. So, hemoglobin is a structure that is contained in our red blood cells. It's really important structure because thanks to that our blood is able to transfer O2, meaning the oxygen in our blood, to our tissues really effectively. The oxygen dissolved in our plasma itself wouldn't be sufficient for the demand of our tissues for the oxygen. So it's really essential to have this transferring structure for that O2 and as well for the carbon dioxide, because it takes the carbon dioxide back from the tissues. Carbon dioxide is a product of metabolism there, and our tissues can get rid of the carbon dioxide thanks to the hemoglobin. I'm right ahead in my head, thanks to the hemoglobin. So that's why the function of hemoglobin is essential. Let's take a closer look to the structure of hemoglobin. So it's right in the name of it. So the first part that makes the hemoglobin is heme. Heme is a structure with iron ion contained in the middle of the structure, and one hemoglobin has four hemes. Oxygen binds to this heme part, so you can carry 8 atoms of oxygen in total, because we know that oxygen pairs into a molecule of two oxygens in one molecule. And just imagine that you can have one molecule of O2 attached to one of these green little things, which is heme, and that's how the oxygen is transferred via the hemoglobin. Next part is the globin. The globin part is a protein. To make it simple, it's protein. There are four protein chains, and to the terminal groups, NH2 groups, which is like amino acids contain the NH2 groups, and to the terminal NH2 groups there is CO2, meaning carbon dioxide, binded to these parts. So the carbon dioxide binds to the protein part, while the heme or the oxygen is bind to heme. So that's the key difference, which is quite important to remember, and they ask about it a lot in the test questions in med school. So that's why I'm mentioning it. This is a closer structure of the heme, which was the green structure on the previous slide. And what's important here is that it needs to contain the iron ion in the middle in the oxidation state +2, because if it's contained in oxygen or oxidative state +3, the heme is not able to carry oxygen. Therefore, it loses its function for oxygen transfer, which is really bad, because then you get hypoxic, your tissues don't have sufficient amount of oxygen, and it's just bad. Like the processes in the tissues cannot be going on, and they lose their function, and you can potentially die from it, because we all know that if we don't have enough oxygen, we can die. Now, what causes the shift from oxidative state 2 to oxidative state 3 of the iron ion in the middle of the heme structure? First, it can be nitrates. It's one of the structures. Many structures can do that, but nitrates are one of them. So what they do is that they change the oxidative state from +2 to oxidative state +3 in the middle of the heme molecule. Then, how the modified hemoglobin is called, it's methemoglobin. Well, what happens in a human body that is older, let's just say 6 months, 6-ish, I believe so, we've got enzyme. We've got enzyme that's able to transfer methemoglobin back to regular hemoglobin. The enzyme is called methemoglobin reductase. It's essential because you cannot have more than certain percentage of methemoglobin, of like your total content of hemoglobin, because otherwise, as I just mentioned before, you can actually die from this condition. So the problem with newborns that are younger than 6 months is that they don't have the enzyme in sufficient amount in their liver. Therefore, they are not able to transfer methemoglobin back to the regular hemoglobin, because that's what they need, the methemoglobin reductase, that they just don't have sufficient amount of it yet. So that's where the problem arises. Well, the main issue is in that the nitrates are contained everywhere, also in the tap water. And why are they there? You might be asking. Well, they usually get there from the fields because plants are using the nitrates as their building material to synthesize amino acids, which is their, it's like a building brick. They need to build themselves through that process. So that's why they need lots of nitrates. So they are also artificial in the nature, in the fields and stuff. When you want to really grow the stuff, that's why you use the nitrates to kind of support that growing stage. And they also are found in nature naturally. So we've got two ways how to get the nitrates into the nature, and then you can imagine it's raining and it just takes all the nitrates from the field and from the nature to the water source, and that's how it gets to our households, and that's where we have the problem. It can actually be really dangerous for small kids and babies, newborns, as I said before, so because they can become hypoxic and their tissues are just not sufficiently supplied with oxygen, and that's where the problems arise. That's why we use the packed water, which is used for babies. I mean, everyone can drink tap water. You have probably done it also while being on vacation in some countries that have not so good hygiene there, but it's essential for babies if they are not drinking, breast milk, and if you need to prepare them the artificial milk. They just need these bottles need to be made with packed water and not the tap water, because it contains the nitrates even after you heat it up over 100 degrees. It just still contains the nitrates that can be really dangerous because of the insufficiency of the enzyme in baby's liver. Please support me through subscribing or liking or turning on notification. I will be grateful for that. Hope you learned something new, and I will see you next time.